There we go. Okay, so last time we were able to talk about how do we find the area between two curves that intersect at more than 2 points, right? So it could be something that looks like this, right? And we found out that it's still the same thing. You just have to figure out where they intersect and which function is on top and which function is on bottom, right? So you could have, for example, a graph that might look something like this. Like, let's say I have a graph that looks something like this, where one function does this, right? And another function does this and intersects maybe somewhere off over here, right? So you have an intersection here as well as this one right here and this one right here. But for this one, I would need to split this up, right? Because the blue function in this particular example remains on top the whole way through. So if this is A, this is B, and this is C, I don't need to break this up into A to B and B to C because it wouldn't change anything, right? It would be from, let's say, from A to B, and let's call these functions, this blue one, let's call this blue one f of x. Let's call this red one g of x. Right? It's still the same concept of like taking the top function minusing the bottom function, right? When you do this integral to see the distance between the two, right? And then adding it to the same exact thing because over here from B to C, the top function is still f of x, right? F of x minus g of x. And we know that from our properties of integrals that if I'm just adding these two together and it's the same functions inside, I could just do the integral from A to C of f of x minus g of x, right? So just because they cross at more than 1 point, it doesn't really necessarily mean that you have to break them up. But if they cross and then they switch between which function is on top and which function is on bottom, then we need to pay attention to that and split up the two areas, right? Split up the two functions here because this, like I said, it's very simple. Just keep the top function minus the bottom function when you do those integrals, and you'll get the area of those regions, and that's pretty much it. Not to split off from just, not to split off from the other idea of like finding the area between two lines, right? It's not that crazy, right? To get that region right there, it's always top function minus bottom function. The only thing that might trip you up, and they might do this on the AP exam, it is fair game, is that they might give you the equations in forms of x equals to y. So it's a function of y instead of a function of x. And that, in those cases, you just kind of have to like tilt your head sideways and look at it and see which function is on top when you tilt your head to the right, right? You see right here, this red one is clearly on top. I put that in quotes last time. So those are little things to keep in mind. They're all the same concepts, right? When you're looking for area between two curves, you just have to try to like figure out and find your way of looking at the function to see which function's on top. Okay, but yeah, for these ones, I don't think I've seen ones that cross multiple times where they do it as a function of y, meaning you have to tilt your head to the side to see which one's on top. Most of the times it's in a function of x, just so you don't have to deal with the extra rotation of it. But you do need to pay attention to where the functions cross each other and when one becomes the top function and the other one becomes the bottom function. Okay, that's that. All right, let's get into a new one today. Today, we're going to be talking about, whoa, that's weird. Let's go with that. I'll click here. There we go. Stop it. I have a keyboard already. There we go. We're going to be looking at volumes with cross sections. Volumes with cross sections. So notice everything we've been looking for is an area, right? It's the area between two curves. It's the area between the curve and the x-axis. It's just a two-dimensional thing, right? A two-dimensional thing. So, right, when we had something like this, let's say I have just a simple function. Let's say it looks something like that, for example, right? Whatever that function may be. And when I found the integral from 0 to wherever this crosses, like so, right? That helped me calculate that area, like that, right? Today, we're going to go into the three-dimensional zone of calculating volumes that are formed based off of a base with this area. And there's different shapes that come out of these things, right? so I'm going to have you picture something in 3 dimensions a little bit here. Can you guys imagine, we're looking at this straight on, right? And in the 3rd dimension, popping out of your screen is a square that is formed with the sides from here to here. Can you picture this real quick? So picture this line right here, this distance right here, right? And I want you to imagine a square that has a height that's the same length as it is from this point right here to this point right here. It's popping out of the screen. Can you picture it? And if you can't picture it, then don't worry about it too much. But it's a little hard to see. Okay, so let me try to. My 3D drawing skills are terrible, so I'm going to try my best to try to get you to see this. So this right here is my y-axis. This right here is my x-axis. What I'm trying to show you is that I want you to imagine, right? Like I said, a square popping out of that. So if I were to draw this in a like this right here, imagine that. Oh God, and let me try this again. This is my x-axis right here. This is my y-axis, right? Picture that it's a little bit flat now, right? And my z-axis is coming out of this thing like this, right? That's my z-axis. Okay, let's make that a little bit bigger. Right, it's coming out of this axis like this. Whereas if you're looking at it on this drawing right here, it would literally be coming out of the screen, right? So, man, I can't wait for the day where we have like 3D rendering. So then when I draw stuff like this, you guys can just see it popping out of the screen, and then you could go around and look to the sides. But until that day, here's this one right here, right? It's on its side, like so. That's that area right there. And I'm saying, can you imagine, right, that we draw a square based off of this length? So whatever this length is going to have that height popping out of it. God. Okay, sorry. I apologize if my drawings are bad, but like that right there. Can you guys picture this square? Can you guys see it? God, that's terrible. Oops. Let's try this again. So it's coming up like this. And it's going like that. So, can you see it? Ryan, you see it now? All right. So check this out. If you can look at this, right? This is, if you think about it and you kind of look at that slice right there, it's like a very, very thin slice, right? It's a very, very thin cut, right? Super, super thin, but you can calculate the area of this blue square that's popping out of this drawing, right? Oh, thank you, David. I appreciate that. Now, what I'm going to have us take a look at is the three-dimensional shape that gets drawn from this. If I were to do this infinitely many times from beginning to end, so if I go from this point right here, right, this right here, as you can see, is a smaller distance, right? It's a shorter distance from here to here. So the height of this square is only going to go up about, oh, I'd say about this much and this far, right? And then if I went from here to here, it would be even smaller than that, right? It would be even smaller than that. It would be like that big, right? So what I want you to picture now is infinitely many squares that go from here to here, from the back where it first starts crossing, which is like this bigger square, all the way down to the front right there. Can you see the shape? It's like, well, it's kind of hard to see, but it makes this three-dimensional shape. And if you do it infinitely many times, we can actually calculate the volume of that thing, right? We can actually calculate the volume of this. So how do we calculate the volume of something that looks like that, right? So what I've essentially done is like I made a couple more wedges here, a wedge here, right, and another wedge here, like so. So what we can do here, right, is let's take a look here. Let's write this out. I'm gonna go back to practice my writing skills here. 4, right, cross sections of area A of X, right, taken perpendicular to the x-axis. Can you guys understand what I just wrote down there? This shape right here, right, is perpendicular to the x-axis. What does that mean? Right, if you look at this x-axis right here, that shape is cutting it and forcing a nice little right angle. You see that? Monica, would it be a triangle? It's like a triangular, yeah, it looks like a triangular prism, but it kind of like curves because of the side right there, right? So this curve kind of side, that side kind of curves a little bit. I'll show you a nice 3D rendering of it so you can see what that actually would look like once it's all filled in. So you can kind of get a better picture of it. Pizza slice, except it's a very thick, like height-wise pizza slice if you want to look at it that way. Because yeah, let me show you that in a little bit here. But here, if you are for cross sections where the area of the cross section is taken perpendicular to the x-axis, you can actually calculate the volume of this shape by simply taking the integral from a to b of the area that it's in question. So if you were to look at this blue shape up here, right, the area of each of these cross sections, right, would be equal to whatever the function is, right, whatever the function is to give me this distance right here, right, whatever that distance is, squared. So let's pretend this function was called f of x, for example, right? So the distance from here to here, the length from here to here, would just be whatever that f of x is, right? Whatever that function is. So if I take that function to give me this distance right here, and I square it, that will give me this area of this little cross section, right? So that's what this a of x represents, is calculating the area of those little cross sections. Now, we've talked about this, right? If I can picture infinitely many cross sections from beginning to end, and I just add them all up, that's what the integral is. The integral sums up all those little cross sections together infinitely many times, right? They're thinly sliced, and they punch them all together and they add them all up, and that will give me that volume of that three-dimensional shape that you guys are still trying to picture what it looks like. So let's take a look at what this would look like. Okay, give me a second here. Geogebra. Let's go over here. So there's a website. Let me put it up here and share it with you, called Geogebra, that people love coding on, which is kind of neat to look at. So as you can see here, on here, you can kind of like graph whatever graphs you want, right? Let's see here if I can get one that looks like the one that we did earlier. Give me a second here. Let's go with equals to 0. And let's go with this one up here equaling to negative x squared plus 3. Is that going to work? That'll work. So here to here, and then from here to here. That'll work. Okay, so you guys can kind of see this, okay, right? Is that all right? So this right here, the drawing on the right here, right? This is what I'm sorry, the drawing on the left right here is the two-dimensional drawing, right? Two-dimensional drawing, you can see it, this parabola right here, and then this right here is going across. The one on the right, what's cool about this site is it works in 3 dimensions. You see it? I can tilt it down so we can lay it flat, right? Like so. I can spin it so it spins automatically. I get dizzy whenever I see this, but you can kind of see it, right? So it helps us to see this thing in 3D. What's neat is, if you look here, the cross sections that we're talking about right now, we're talking about a square, right? So when I slide this along here, you can see the square getting bigger as it gets over to here, right? And then it gets smaller as it gets over to here. Now, what does that shape make for us, right? What does that shape make for us? Well, if I click here and click solid, and I have it to, let's say, about 4 rectangles, you can see the rectangles the squares that get formed as you move along here, right? So you can see the base of your cross section is dependent on how far away your function is from the x-axis, right? or whatever it is that you're measuring it between the two. And whatever that base is, adjusts the height of the said square. So you see right here where the base is super wide, your square is super high. And then when you get down to here where your base is a little bit smaller, your squares get smaller as well. Now, what would that look like? So Monica had a guess of like, is it a triangle? Right? David's saying it's a pizza slice. It's going to look something like this. Now, I don't know how I would describe what that looks like, but that's what it looks like. Do you guys have any ideas? What would you describe that as? They do have names for these, by the way. I just don't know them. But what would you describe it as? One of those Lego pieces. Yeah, I can see that. Which now leads to this interesting idea. Monstrosity. One of those Lego pieces. But check this out. If you can see that a cross-section of something that's three-dimensional makes some kind of shape, you can calculate the volume of that said thing. Now, you might not think that's a big deal because you're like, nah, we've calculated volumes of things all the time. But those things you calculate volumes for are very, very basic ones, right? You guys usually calculate volumes for like cylinders or the most complicated ones is probably like a pyramid, right? Those ones had preset values. If you know what the length of something is that's fixed, you can calculate those volumes fairly easy. But when you get shapes that are not like that in the real world, which is, you know, sometimes it's not going to probably look like this one, but there are shapes and buildings out there that do have cross sections that you can kind of find with calculus and integrals. You can calculate the total volume of that thing. This is a neat one to look at right here. Give me 1 second here. Let me get this picture over here. Some buildings are based off of these things. And let me show you this building right here. Check this out. Let me make that a little bit bigger. This center in Kansas City, right? The Kaufman Center of the Performing Arts. Look at this building. You see the cross sections here? Those cross sections are not squares, though. Those cross sections are what? Can anybody tell me? What do you guys think that cross section is? What do you guys think? They're clearly not squares, right? But they are cross sections. Can you guys see it? See it? Ovals? Yeah, like semicircles, right? Like semicircles. Half a circle or a quarter circle. And check this out. Right? If we go with the semicircle, we can go like this right here. Take off the square, take off the solids. And let's go ahead and move that over here. So if this is your base, right? Your circles, right, would be based like that. You see that? With your diameter being the base. So it looks something like this. You see it? So there's different shapes here that we can take into account. So the problem with these things, or I mean not the problems, on the AP calculus exam, this is a very common type of problem that does show up a lot, where they're going to ask you to calculate volumes of things. And most of the times they'll focus on the cross sections to be familiar shapes that you should kind of know, whether it be a square, a rectangle, a semicircle, or several varieties of triangles. Like it could be like an equilateral triangle, it could be an isosceles triangle. There's a lot that goes on in there. But with that to be the case, in order for us to do this, we're still going to be taking the integral of that area function, which means you need to know how to calculate the area of a square, the area of a rectangle, the area of a semicircle or a quarter circle or a triangle. Okay. Do you guys know those formulas by any chance? Do you guys know how, like right here, I wrote up here, the area for a square is the sides squared, right? If you know what the side is, you just take the sides and you square them. Do you guys know, for example, like, you know, the next one should be an easy one. Another easy shape that we were talking about is rectangles, right? If the cross section was not a square, but instead was a rectangle, how would you calculate the area for that? Right, the area for a rectangle, right? Hope you guys realize it. It's just something that looks like this, right? Where you have the base and the height, or the length and the width, depending on how you label it. And Monica's going with length and width. I'm going to go with that as well. Length times width. And it's your job to figure out what's the function for the length of your rectangle and the width of your rectangle. And usually they give you some type of relationship between that. If you look at, yeah, you try to see that, the rectangle is like, sometimes they'll say the width is equal to half of the length, or, you know, it's double the length. It depends. You got to be able to read those problems, right? They also include things like semicircles. Semicircles, right, is just half of a circle, right? So the information that you need for this thing right here, right, area of a semicircle, well, area of a circle is pi r squared, right? That's just the area of the circle. If it's a semicircle, you just take half of it. You just take half of it, right? So a semicircle goes something like that, right? And what you need for this particular case, then you need to find out what the heck is the radius, right? How do you find the radius of it based off the function that they give you, right? There's that one right there. And the last one, of course, is the triangles, right? Triangles, area is equal to 1/2 base times height, right? And this is going to be wildly dependent on the type of triangle that you're dealing with. If you just have a right triangle that's coming out of there, right, then the height and the base, they need to give you some type of relationship between the two, so then you can find it. If it's a equilateral triangle, then you know the base is going to go from whatever here to here is, but the height is going to take a little bit of work to find, right? There's equations, by the way, that tell you the height of an equilateral triangle if you know the base. Same thing with an isosceles triangle. If you know the base of an isosceles triangle, you can find out the height of it if you're given this other two sides. And I like deriving it. Like I said, I don't like memorizing equations, but we're at the point where I don't think we have enough time for me to show you how to derive those things. So instead, later on, I'm going to just give you those equations. So if they give you an equilateral triangle, you know that, hey, this is the equation to find the height for that, and if they're given the base. But yeah, once you get these areas down, right, for these different shapes, all you need to do is then take the integral from one part to the other. Okay? So let's do an example. Let's do an example here. Okay, so let's say I have here, right, I'm asked to find the volume, of the solid in which, that B's throwing me off there, let me get that out of the way, in which the base oh my god, in which the base is the region bounded by the graphs of, and here are the graphs, let's write these down here. First one up is f of x is equal to negative 1/2 x plus 1. G of x is equal to 1/2 x minus 1. And x equals to 0. So let's take a look at this one right here. Okay. So let's break this up into parts here. First part, let's call it part A. Let's say I was asked to find the area where the cross sections are squares and perpendicular to the x-axis. Okay. So there's a lot going on in this problem, right? We're looking for this three-dimensional shape, and we're trying to calculate the volume of this three-dimensional shape. Okay. Now, before I even do that, when you deal with these types of problems, it's really ideal to graph it out. Like, sketch out what the graph should look like in just plain two-dimensional shape, in two dimensions. Okay. So I'm gonna sketch out this graph right here on the side. You okay, dog? Yeah, you okay? Okay. So let's graph these guys out here. So first things first, right? I like graphing this one first because x is equal to 0 is a very easy vertical line right here at the y-axis. So it just goes something up and down like that, right? So that's the first line. Let's go with the next one. Let's do this one in blue. Let's say f of x right here is equal to -1/2 x plus 1. That's a linear line that goes up at the y-intersection of 1, right? And then it kind of goes down 1 and over 2. So about there. So that's just this line right here. Boom. Right? And then we have this one over here, this g of x function we have going on here, which is 1/2 x minus 1. Again, linear function, right? Has a y-intercept of -1, which is about, I don't know, about here. And it's going to go up 1 and over 2 with the slope. So it goes up 1 over 2. It crosses at that point right there. So it forms something like this. That didn't look as good. Hold on. Get that nice and straight, knock me. Boom. There you go. So if I was just calculating the area, right? If I was just calculating the area, right, between two curves, would just be the integral from 0 to, it looks like they cross at 2 right there. So it'd just be from 0 to 2, right, of the top function minus the bottom function, and then I'd be done to get the area between those two. But this is not asking for that area. This is asking for the volume, right? And the cross sections of the squares are perpendicular to the x-axis, which means if I were to draw this square, I'm not drawing it this way, right? That way would be perpendicular to the y-axis. These squares are perpendicular to the x-axis, so it would be a square that has this right here. Let's not do this in blue because I'm already drawing in blue. So let's go with purple, right? It would be this right here. This is, this right. Geez, knock me, your hands are so shaky. What the heck? Hold up. There we go. Shaky hands. Okay, so can you picture it? The cross section is a square, right? And it's perpendicular to the x-axis, but it's popping out of the screen right now. Can you imagine it? So from what we saw earlier, it's just popping right out, right? Instead of it being like a curved line like this one up here, right? But with those squares, it has this nice little triangle base, but there's squares that are coming out of it. You guys imagine it? You got it pictured in your mind? If not, let's go use our 3D rendering program to take a look at it. Or do you guys want to? I would love to waste time and show you guys. I've actually gotten pretty darn good at drawing these three-dimensional shapes, I have to say. But I think I'll just show it to you with the software rendering instead, because time. So let's go take a look here. Right, for this site to work, you got to plug in those equations. As you notice, though, I don't really have space to plug in 3 equations onto this site. I can only plug in 2 equations. So I'm going to plug in the 2 main ones that make the line right there. And actually, I lied. I already did this over here. Let's take a look over here. I think I did it already. Yeah, I did. Here it is. So here we go. Right? So right here is the drawing that we already have. And then in 3-dimensional shapes, right here, like so. Knock me, get it together. I'm struggling here to control my 3-dimensional drawing. Sorry. Sorry, guys. All right, so here it is, right? And we're looking for our base to be a square, which looks like that, right? Popping out of there like that. See, so it's going across like so, right? Now, can you picture it? Let's go ahead and make this a solid. And this is what it's going to look like if I fully form it. It's like a pyramid, isn't it? But the base right here kind of like changes what that looks like. I'm going to go ahead and screenshot this and put this into our notes. If you guys want to, you can screenshot it as well. Unless you want to practice your drawing by hand of this thing. Let's go with, let's not make it all the way full. Let's just make it so we can kind of see the difference between the two there. And I think that's a good shot of it. Jeez, knock me. Wait, what if I rotate this way and zoom this way? God, I can't get the right angle that I want, but I'm just being too picky. Let's go with this one right here. This looks good. Let's screenshot you. Bam. Let's get you into our notes right here. Bam. And get you right there. So that's what that should look like, right? Cross sections are perpendicular to the x-axis and they are squares right there. Okay. How's that look? That looks okay? So my question to us, or my question for this problem here then is, in order for me to calculate this volume, whenever I copy and paste, only someone who sees this can tell me why OneNote does this. Copy and paste, and it just does not allow me to go in there and change my pen settings. Anyways, so in order for me to calculate this volume of this thing, right? Remember, the volume is simply just equal to the integral for this particular case. It's going to go from 0 to 2, right? Because it's crossing here from 0 all the way up to 2, right? Like so, of the area of this function, right? Dx, right? Now, how do I calculate the area of this function? Well, this length right here, right? That length right there, if you look at it, the length of that side is equal to, how do I get this length? Anybody have any ideas? How do I know what the length is from here to here? Well, I look at the top function. This top function is f of x. This bottom function right here is g of x. How do I get the length from f of x to g of x? Anyone have any ideas? How do I get that length there? Because that's the length that's going to help me figure out the length of the side of your square. And it is going through the x-axis. It is going through the x-axis to get from there to there, right? So my question, maybe if I redraw this over here, let's say I had something that looked like this, because not the x-axis itself, but let me just ask you this point right here. If I had a point that was right here at 2, 5, and another point down here that was at 2, -1, how far is it from here to here? What was this? What would that length be? How would you calculate that length? Anybody know? If this was a different scenario here, this is 5 and this is -1, how do I calculate how far away those 2 points are? Anyone? How can I tell how far away that is? Does anyone know how far away that is? Brian's got the right idea. You just made it a little bit more complicated for yourself. You subtract the two, right? Whenever you're looking for distance between one point and another, you just subtract them at the absolute value of the y-axis. Yeah, that's the just subtract the two. You don't need to. Okay, so think about this. Distance between 2 points is always the difference between the two. You just subtract the two. Now, some of you guys are going and you're overcomplicating this by doing the absolute value. Here's the problem with doing the absolute value of that. What happens if that point was not up down there, instead it was down here and it was at 2, 1? What's the distance from here to here? What's the distance from here to here? All right, if you do that, what you just wrote down, it's going to give you something that's not the right distance, right? So when you're calculating this distance, we just need to subtract, right, the values from them. Yeah, that's pretty much it, to subtract from here to here. So this would be 5 minus 1, so that's a distance of 4, right? So that's the idea here. We're just subtracting the y values from them, right? We're just subtracting the y values along the way here. So the length here in purple is, if I pick any random x value, let's just say this is the x value I picked, it's going to be f of x minus g of x, right? That's how I get that length right there, which we already have those functions, by the way, right? We have those functions. I can write that down. F of x is equal to -1/2 x plus 1, right? And I'm going to go ahead and subtract that from g of x. And g of x is 1/2 x minus 1. So the length between those two sides right there is going to equal to 1 half x minus 1 half x, that's just going to give me negative x, right? 1 plus 1 is going to be plus 2. So that's the length of this side right here. That's the length from here to here. From here to here, it's negative x plus 2. Right? I took this function up here that was negative 1 half x plus 1, and then this function down here, which is positive 1 half x minus 1, and I subtracted those two to get the length there. Now that length is not the area of this green square. That length is just this length right here, right? This length right here. Now to get the area of the square, I just take that and I apply it to this right here because it's a square, and I just multiply those two together. In other words, I square the sides, right? I square the sides. So this is the side. I'm just going to square it. So for me to calculate the volume of this thing, it's going to equal to the integral from 0 to 2. And my area in here is going to be negative x plus 2 squared dx. That's it. The reason why it's squared, well, to get the area of a square, you take the side and you square it, right? So if I'm looking for this particular one right here, if I know that the base of it is negative x plus 2, I just take that and I square it, and then that should give me an area of one of these little squares. When you do the integral from 0 to 2, you're going to add up infinitely many squares along the way to give you the volume of this three-dimensional shape. And that's pretty much it for when you do these types of problems. So you're just calculating that. And you get set up with this nice little integral that hopefully you guys can see. It's, well, it's an integral problem now. You either do u substitution for this problem, right? Because it's something squared, or you can FOIL it out and then just do the power rule. It's up to you however you want to calculate this integral. But now it just comes back to this whole thing that we spent an entire 2 chapters on, but now we're just applying it, right? We're just calculating integrals for these set specific things. And that's all it is. We've been practicing integrals, and you're just going to keep going and doing more integrals. That's all this ever is. It's like you learn what a derivative is, and then we apply derivatives. Second semester, we just learned what an integral is. We're just going to be applying integrals and figuring out different ways to calculate these integrals. So anyways, I'm going to FOIL this out. I like dealing with it FOILed out instead. So this is going to go from 0 to 2. This is going to give me x squared, right? Negative 2x is going to give me negative 4x, right? And we have here a plus 4. Now, Ryan just asked a very good question. Where did the square come from? Where did the square come from? Remember, we're looking for the area of each of these green squares that we have there. Now, those green squares have a length, have a base of this purple line right here, which is negative x plus 2. For this to work, for me to calculate this volume right here, I need to calculate the integral of the area of each of these squares. Yeah. So I take that length that I have right there, and to get the area that I'm looking for a square, right? This is important. This is the area for a square. I take the sides and I square it, right? That's all it is. It's the squares of the sides, right? That's what S is. And that's the length of the side, and that's in there. And that's where that square comes from. Awesome, awesome. Good question. So that right there becomes this dx, and I squared it out so it's easier to do the integral. If you guys prefer the u substitution method, you can do u substitution here and let u equal to negative x plus 2. du is equal to negative dx. And you could actually integrate this with u substitution, but I'm just doing it this way because this looked easier. This looked easier. So I'm going to go ahead and integrate this right here. This is going to become x squared is going to become x cubed over 3 minus 4x. This is going to become x squared. So this is going to be 2x squared to give me that 4x when I take the derivative. And this over here is going to be plus 4x right there. All right. This, of course, is being evaluated from 0 to 2. Being evaluated from 0 to 2. I just take those numbers and plug them in like so. So I have here 2 cubed over 3 minus 2 times 2 squared plus 4 times 2 minus, well, I hope you guys can see that if I plug in 0, this is just going to come out to 0, right, for all those x terms right there. So I go ahead and write this out. Let's evaluate this. 2 cubed is going to be 8, so this is going to give me 8 over 3 minus 2 squared is going to give me 4. 4 times negative 2 is going to give me negative 8. And then 4 times 2, that's going to give me positive 8. So my answer here, when I simplify this all out, that volume is going to give me a volume of 8/3. And that's my answer. So the volume of this particular green thing from here all the way to there, this weird looking pyramid, is going to be 8/3. And that's it. We can apply these integrals to now calculate volumes of three-dimensional shapes. Right? Not too shabby. Yeah, not too shabby. All right. Let's not put this to waste here. Let's go ahead and continue with this one right here. You guys have that written down? I'm going to scroll down to the next one. Or actually, I'll scroll down just a little bit so you guys can still copy this. I'm going to write down the next problem. Let's go with part B here. Part B. Let's say we're looking at the same problem, but let's say now the cross sections, right, perpendicular still to the x-axis. But this time, instead of squares, they are semicircles. They're semicircles. They're half circles instead. Right? They're half circles instead. So same scenario, right? Same thing up here. Let me see if I can copy this. Whoa, 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 whoa. There we go. No, I missed that part. Let's get that black line right there. There we go. I'm going to copy this and put this down here so we can reuse it. Boom. Okay. Now, instead of them being squares, let's say that the cross sections now are going to be semicircles. Did you guys finish copying this down? Are you guys okay? I'm going to scroll down here and move on. Okay, because that problem's done, right? That problem is done. But now let's take a look, see if we could figure out what it would look like if the cross sections were semicircles instead of squares. So again, I'm not going to make you sit through and watch me draw that shape. Instead, I'm going to just put it up to, what's a good view of it? Would it be like this? This type of projection. Huh. Anyways, let's change this. So instead of it being a square, let's take that out now. And let's say it was looking at a semicircle instead. So it looks something like that. And again, if you looked at it as a solid, right, and we increase the number of it, it looks something like this. What does that look like to you guys? You guys see it? What does that look like? Half a cone. Yeah, half a cone. Are you guys starting to realize yet that they use calculus to help you calculate those volume equations? The volume of a cone, do you guys know what the volume of a cone is equivalent to? Well, now that you know calculus, you don't have to memorize that formula. Instead, you can just calculate it yourself. I'm going to make this a little bit smaller there so we can see it like that. Let's go at it from that angle, like that. There we go. That's the good one. Let's go ahead and screenshot that. I'm going to put this in our notes. So, put that right here. Oh, that's beautiful, isn't it? We got our base drawing right here. We got this right here. So, again, to calculate the volume of this, right? The volume is just going to be equal to the integral from 0 to 2 of the area function, right? But the area this time is not equal to the side squares, right? Since this is a semicircle, what's the area of a semicircle? Does anybody know? We wrote it down earlier. Area of a semicircle. Well, area of a circle is pi r squared. Semicircle is half of this, which is just going to be what? Hopefully you guys know it. It's 1/2 pi r squared. Yeah, 1/2 pi r squared. That's right. That's right, David. So that's what the area function is, but I need to know what the radius is. What's the radius in this problem? The radius in this problem is not this length, because this length goes all the way across. That length, in this particular case, happens to equal to the diameter. Diameter is going from f of x minus g of x. That gives me the whole diameter. Take that length, Brian is saying to go ahead and take that length and divide it by 2. So we found out that f of x minus g of x was negative x plus 2. If I want, that's going to be what the diameter is, right? Which is negative x plus 2. So he just says take that and divide it by 2. Bam. That is my radius for this circle right here, right? For this circle that's going across like that. All right, so to get that radius right here, that goes across right there, that radius is just going to be from here to here, which is half of the length from f of x minus g of x. See that? F of x minus g of x. For that to be the case, right, we just plug that in here. So my area function is going to be equal to, I'm going to put this as a one whole thing instead of 1/2 pi. I'm going to write that as pi over 2. And my radius is going to be negative x plus 2, but in order to calculate the area, I'm going to have to square that. So when I do this integral, right, when I do this integral over here, this is going to be the integral from 0 to 2 of pi over 2 times negative x plus 2 over 2 squared dx. Of course, I don't know if you guys can see this or not, but the pi over 2 is just a coefficient. And I can also square everything that I have here, right? So check this out. I can actually do a little bit of math here. When you have a fraction like this, you can square the top and square the bottom. So I can rewrite this. This is going to be the same thing as pi over 2 times the integral from 0 to 2 of negative x plus 2 squared over 2 squared, which is going to give me 4 dx. And I can take that 4 out as well. It's just another coefficient, right? There's no x's in that denominator. I can write that out in front. So I can go ahead and multiply that out to the front of my integral. So I can write this as pi over 2 times 4 is going to give me 8 times the integral from 0 to 2 of negative x plus 2 squared dx. Which, by the way, we've already did this earlier, right? We already did this earlier. You could do u substitution. You could do... you can FOIL it out, however you want to do it. Since we did FOIL it out earlier, we also, by the way, know that this integral is going to be 8 over 3, but let's just show the work here. Let's go ahead and let me show you a different method. If you go ahead and do u substitution and let u equal to negative x plus 2, du is equal to negative dx, or in other words, negative du is equal to dx. I can do this integral right over here. All right, so this becomes the integral from 0 to 2 of u squared times negative dx du. Oh, you're not happy with the u substitution? No, you're not. Oh, it's okay. You don't have to like u substitution. You wanna go out there and bark at whatever it is that got you going? You wanna go find Angela? Oh, dog. All right, sorry about that. Where did that 4 come from? Brian, he squared the denominator. Thank you, Brian. This 4 over here, I squared. So this, you can, when you're squaring a fraction, you can square top and then you can square bottom. So that's what I did. I squared top and I squared bottom because I saw that there's no x terms in there. Anyways, let's do this integral. Just show that this is actually going to equal out to this. So this is going to be negative u to the third over 3, right? But I'm going to go evaluate it from 0 to 2, but I need to replace that u back with what it was equal to, which is negative x plus 2 cubed over 3. And there's a negative there, evaluating this from 0 to 2. Does this work out okay? So over here, I'm going to have negative 2 plus 2 cubed over 3, which is going to be 0, minus negative 0 plus 2 cubed over 3. This goes to 0. This is going to be plus, because the negative and negative cancel each other out. 2 cubed is going to be 8 over 3. Ah, it comes out to the same answer as what we found earlier, 8 over 3. So we know that, I mean, I don't know why that surprises me because, you know, it should be the same thing because it's the same problem. I don't know. I like math surprises me sometimes. But this right here, we already did earlier, but I'm showing the work right here. It comes out to be 8 over 3 just to show it again. So my answer is going to be pi over 8 times 8 over 3, right? Which is going to equal to pi over 3 as our final answer. So the area, the volume of that half cone, is pi over 3. That's pretty much it. Kind of neat, right? So yeah, let me see here. Let's do another one. Same problem, but let's say the cross sections is something else besides a semicircle. Let's go with something a little bit more difficult. Actually, I'll show all these ones here. Whew. Okay. Are you guys able to copy that down? I'll zoom out a little bit more so you guys can copy that all down. Go on to the next problem. All right. Hopefully you guys are able to copy that down. Let's go on to the next one. Let's try another one. Let's go with, this time, let's say the base is, instead of a semicircle, let's say the cross sections perpendicular to the x-axis are, this time, let's say, rectangles whose heights are 3. Okay. So this time they're going to be rectangles instead of semicircles, instead of squares. And the heights are set. They're constant heights all the way through. So I'm going to go ahead and take this drawing again. Copy it. Bring it down here. Paste. Ugh. Why don't you automatically come with me? Come on, OneNote. You can handle it. You can handle it. There you go. There we go. There we go. So that's that drawing right there. Let's go ahead and zoom that in a little bit more so we can see that a little bit better. But this time, the heights are just going to be a rectangle with a set height of 3. Okay. So can you guys picture what that looks like in your mind? That line right there is popping out of the screen vertically straight at you, and then if you tilt your head, you'll see that it makes a rectangle with a constant height all the way across of 3. I don't think this will allow me to do that. Yeah, this site, I don't think it'll allow me to do a rectangle that has the same value. So sadly, I don't think this is going to render it okay for me because it makes the rectangle. Dang it, that's the ratio. Yeah, it won't just let me do 3, huh? Because then 3 will just make it 3 times the size. Yeah, that's not what I want. I want it to equal to 3. So I don't think this site will actually get me to do it. Will not actually do this for me. So what I'm going to do instead is screenshot this and try my best to draw this by hand. I'll try that again. There we go. Boom. So let's go ahead and put that in here. And let's try our best to draw this out by hand here. So it's a rectangle whose height is 3. So it would be going up like so. and then going across like so. So it'd be something like that. That height right there is 3. So even if I did to here, this height would still go up to 3. See that? So at this point right here, man, that's a little tough to see, but hopefully you guys can see it okay. It goes up like so, but it goes up to 3. Right? So it's going to be something like this. This one just straight up looks like a wedge. You guys see it? I know my drawings aren't that great, but hopefully you guys can kind of see it. Can you see it? Hopefully. Yeah. Now, to get that volume, again, volume, don't overthink it. When you have these cross sections, you're just looking for the integral from 0 to 2 of the area of each of those cross sections. Well, that cross section is a rectangle with a height that's set at 3. So that area, right, is just going to equal to the length of that thing, which is going to be negative x plus 2, because that's what the length is of the base, right? It's negative x plus 2 multiplied by the height, and the height is going to equal to 3. And that's it, right? The length of the rectangle, negative x plus 2, and then the other one is going to be 3. So we just go ahead and, what's my area function? My area function, let's just distribute that 3 right there. This is going to be negative 3x plus 6. So when I calculate this volume, this is going to be the integral from 0 to 2 of negative 3x plus 6 dx. And that's it. And then you just calculate that out and see what you get. Right? So some of these can be a little bit easier, right? Rectangles, squares, I say, are the easier ones. Circles and triangles are the ones that are a little bit more annoying, but you know, it is doable. You can kind of figure them out. It's just a little strange. Sorry. But yeah. So we go ahead and calculate this. I'm gonna be lazy here and actually throw in a little bit of calculator practice. Do you guys, in some of your homework problems, they'll give you functions and they'll say that you need to calculate the definite integral using a calculator. Do you guys remember how to plug a definite integral into your calculator so you can have it do it for you instead? Right? Hopefully you guys remember. Press math, and you go down to option 9. Your calculator can calculate definite integrals and evaluate derivatives for you at specific values if you have the specific value. So if you're on the calculator section, take advantage of that. I doubt that they give you a function this easy on a calculator section. If they have it like a function like this, it's usually on the non-calculator section because you can do it by hand. But still, it doesn't hurt to practice. So this is going to go from 0 to 2, right? And the function we have in there is negative 3x plus 6 with respect to x right there. Let me go ahead and press enter, and it calculates that volume for us, which is going to be equal to 6. But yeah, if you needed to, you could practice this if you want. The integral of negative 3x is going to be negative 3x squared over 2 plus 6x. This is being evaluated from 0 to 2, and you just plug in those values, and it should come out to 6. Should come out to 6. All right. So that's that one. If the cross sections are rectangles, I'm going to show you one last one, which is yeah. Let me show you this one. So let me show you this one. So this last one for this particular example. Let's label this example D. Let's say the cross sections. Perpendicular to the x-axis. All right. This time they are equilateral triangles. Equilateral triangles. Do you guys know what an equilateral triangle is? What makes it an equilateral triangle? All sides are equal. Very good. Very good. Which, yeah, perfect. All sides are equal length. Perfect. Which is awesome, right? for the lengths, the sides of them, and calculating those, seeing that all the sides are the same. But do you guys know the equation for the area of a triangle? The area of a triangle is equal to 1/2 base times height. Now, the base is one of the sides of the equilateral triangle. Awesome. So if you know the length of it, you know the base. The height, on the other hand, is not as easy. The height is not what the lengths are on the side. They are related, and they're related in the sense of, well, let me show you. So first things first, right? Copy this again. Put this onto here. Copy, paste. Shoot right there. Now, if I'm dealing with equilateral triangles, right? The 3D rendering is not that important, but let me just show you just so you guys can see it. Equilateral triangles will look something like this. You guys see that okay? It's another pyramid almost, right? But it's not quite the same. All right, so there we go. So it's this right here. My only issue is calculating those heights. Okay, calculating those heights. So let me take off the solid right there and then just say, like, let's look at just this one piece right here. Let me go ahead and screenshot this. And here's what I want to show you. So for this equilateral triangle right here, right, I'm going to draw it so it's facing us. Right, the equilateral triangle has all the legs equal to each other. I'm really bad at drawing equilateral triangles. So let's pretend that's my equilateral triangle right there, right? All the sides are equal to each other, yeah? So the lengths, are, by the way, are still going to be negative x plus 2. That's what this length is from here to here. That's what this length is from here to here. The length from here all the way to there, right, is negative x plus 2. Now, that doesn't help me to calculate the area of this thing because, again, the area requires the height, like that. See that? So to calculate the area of this said thing, it would be equal to 1/2 base times the height. I have the base. I don't have the height. Do any of you remember how to calculate the height of an equilateral triangle? And it's okay if you don't. It's something that is not a commonly practiced thing, but it is expected of you on the AP exam, which is a little annoying. Because I don't know if you ever heard me say this before, but I used to say it all the time in last year's class. The calculus part is super easy. It's the algebra that's going to be annoying. And this is a very annoying algebra problem if you don't remember how to do it. And yeah, it is not actually tangent. No, we don't use tangent. Actually, you could use tangent. You could. But David, it is going to be a 30, 60, 90 triangle. It is going to be a 30, 60, 90 triangle. There is a 90 degree there. But yeah, we could use tangent though. That actually is something that would make. I just don't want to deal with it. But yeah, this is where you can actually see where the idea of, like, oh man, tangent of 60 degrees is square root of 3. But check this out. Here's the 90 degree right here. If it's an equilateral triangle, hopefully you guys understand that it's equal angular as well, which means it's 60 degrees all the way around, including the very top part. But if you draw a line straight down the middle like this, that top angle right there becomes 30 degrees, right? Because you're cutting that 60 in half. And that's why David's saying 30, 60, 90, because the triangle that's formed right here is a 30, 60, 90 triangle. Whereas it would follow, right, if this was 1, this would be double that, and then this would be that 1 times the square root of 3. Okay? Have you guys seen that ratio before? 1, 2, root 3? It's one of the common, one of the special triangles. The other one is a 45, 45, 90 triangle. But that one goes 1, 1, square root of 2. But anyways, for this particular one, if I know what the base is, then the height is going to be whatever that base is times the square root of 3. Well, this base right here, to go from here to here, right, I cut that in half, it would be me cutting this in half. So this should be negative x plus 2 over 2. Which means then the height, let's do that in green right here, this height right here would be equal to negative x plus 2 over 2 times the square root of 3. That's what the height's going to equal to. It's wild, I know. So the area function, right? The area function is equal to 1/2. The base is negative x plus 2. The height is negative x plus 2 over 2 times the square root of 3. I know. So check this out. Once you get this down and you simplify it, this is what it would look like. This area function right here. I take this 1/2, I'm going to combine it with that half right there. I'm going to get me 1 over 4. The square root of 3, I'm going to put that over here as well. So I'm going to rewrite this as the square root of 3 over 4. I combine those things that I circled right there. And what I'm left behind with is negative x plus 2 and another negative x plus 2. So it's negative x plus 2 squared. So that's that working out there. You don't have to do what I just did there, but people like to simplify things before they do the integral, because the volume of this is going to be the integral from 0 to 2 of the area function that you're looking at of this cross section, which is going to be equal to, you ready for this? The square root of 3 over 4 times negative x plus 2 squared for this equilateral triangle. And then you would just do the integral of this again. This is just your coefficient that comes out, and you do the integral of that being squared. Why is it from 0 to 4? Because I messed up and I have dyslexia. It's 0 to 2. Thank you, Monica. From 0 to 2 of square root of 3 over 4. I was too busy focused on that 4. Because I think it's a very interesting coefficient. The square root of 3 over 4 is always going to be that coefficient when you're dealing with equilateral triangles. And it's always because of this right here. The fact that your 30, 60, 90 triangle, it takes whatever you have as your function and takes half of it and then includes the square root of 3. And when you calculate the area of a triangle, that 1/2 is always there. So that 1/2 and that half of that base turns into that 1 over 4. Every single time you deal with an equilateral triangle. And the square root of 3 will always be there. So I kid you not, some people memorize the area of an equilateral triangle . They memorize this equation. The area of an equilateral triangle is the square root of 3 over 4 times the base squared. I've never memorized this formula, but it comes up quite often enough in calculus that every AP Calc book I've ever looked at shows that equation for an equilateral triangle. I've always memorized the equation for a triangle, and then I derive the square root of 3 part, using 30, 60, 90 triangles. So I leave this up to you. What is easiest for you? Do you like memorizing more equations, or do you like deriving the equations? Either way, you're going to need to know this one, because equilateral triangles, I always try to hope that it never shows up on the AP exam, because squares are easier to deal with, circles, even semicircles are easy to deal with. But equilateral triangles are annoying, but they've shown up quite a bit on the past couple of years. So just get yourself used to seeing that. But once you can get that down, right, the calculus part is easy. We just do the integral of this thing, right? So the square root of the square root of 3 over 4 times the integral from 0 to 2 of, and then you FOIL this out, or, we've already calculated this so many times here, right? This is going to come out to be 8 over 3, right? Do the work there. This is going to come out to be equal to the square root of 3 over 4. Remember, we did this integral already, this integral right here. We've done that so many times. Comes out to 8 over 3. And then you just simplify this out. So this will be the 4 and the 8 cancel out, becomes 2 square root of 3 over 3. And that's going to be your answer for this problem. But I think the bigger point, it's not the answer. The bigger point is, how do you find the area of these particular cross sections, right? These particular cross sections. So they'll ask you all kinds of things: circles, semicircles, triangles, rectangles. Actually, I think that's pretty much it. Those are the 5 right there, which I believe I have a cheat sheet for. Let me see if I have this cheat sheet. I'm going to give you this cheat sheet. I'm going to put it on this notes right here, and then I'm going to give you guys a chance to copy it. But I'm going to wrap it up right here. So when you're dealing with these cross-sectional shapes and you know what type of shape it is, there are equations to calculate the area of those said shapes. So let me go ahead and give that to you right here. I'm going to copy that. I'll put it onto here so you guys can take a look at it. You guys see that okay? So general shapes, right? Squares, rectangles, circles, semicircles, and then various types of triangles. So equilateral triangle is the one I just showed you right here, right? Equilateral triangle is the one I just showed you. By the way, x is if the length of the side is x. So you could replace that with, like in our case, was negative x plus 2, right? So everywhere you see an x, you would put negative x plus 2 for our case, for that particular one. So, you know, you have to find out what f of x minus g of x is. So if you have like a weird function up top and a weird function on bottom, right? If this is f of x and this is g of x, you still do the same thing. You still do this top function minus that bottom function to find out what the length is, right? And whatever function you get, that right there would be placed in for wherever x is. So just keep that in mind. Now, I did not mean to touch that. Now, what the heck is going on there? Stop that. Okay, so once you have that, right, like I said, this... Why are you acting weird? There we go. So what is going on? Okay. Anyways, I only have a couple minutes left. Aside from the equilateral triangle, isosceles triangle is another one that usually gets done in there, but I forgot about this one right here, which is the isosceles right triangle where the hypotenuse is the base. That's a big one right there. If the hypotenuse is the base, then it kind of makes this like triangle thing that comes out of it where the right angle is at the peak of your three-dimensional shape that's coming out of there. But again, you could just memorize these formulas for them, or you can derive them, right? And deriving them takes a little bit more like time to do it, but it's less things to memorize. And that's how I used to do it. I just kind of derive them. But if you don't want to sit down and derive them, you could just memorize these. All right. Anyways, I think that's going to be it for today. Cross sections, right? Volumes using cross sections, not that hard, right? You're still doing integrals from A to B, but what's going to be hard is calculating the area of those cross sections. Okay. So don't let that deter you. Like I said, I'm going to be, actually, I don't know if I'm going to be on campus. I'm going to have to check with Dewey to see if he's going to still show up today. He signed up last week on Wednesday, so I don't know if he still remembers that he signed up. So, but yeah, I don't think anyone else signed up. David, you said you can't make it today, right? I think. So if you can't make it and Dewey's the only one signed up, I'm going to double check. So if you guys want to come, sign up before 12 o'clock. We can do reviews. We can talk about other things. But other than that, if Dewey says he's not going to be there, then I won't be there today. So just double check with me before you go on campus before 12 today, okay? 12:30. Yeah. All right. Anyways, other than that, I'm going to wrap it up here. Have a good rest of your day, everybody. I'll see y'all on Thursday. We're almost done. We're almost done. Bye, everybody.